right, everybody, I think I'm gonna go ahead and get started here. Welcome. This is already week number 3, and I'm always amazed how fast the time goes by, and we will probably notice that again this semester too. Just a couple of announcements here before we get kind of started on everything. I think in my email over, how I send the weekly at the weekend, here's what's going to happen this week. I think I sort of said, oh, the homework is due on Tuesday, unless you want to think about it until Thursday. And I don't know what I was expecting would happen after I wrote that down, but obviously everybody's been thinking now in terms of Thursday. So that's fine. I don't mind. If you're done with the homework, I think some people have already turned it in. That's fine. If you're still working on it until Thursday, it's okay with me as well. I do have office hours later today and also on Thursday, same hours again. So if you do want to talk to me about any of the homework, feel free to do that. I did get the first assignment graded. You probably noticed that. I tend to grade pretty quickly because I just don't, and that's the part of my job. I love my job, can you tell? But there's like one little part of it that I don't like quite as much, which is the grading. If you're going to go into teaching, you'll probably figure this out as well. Any teacher who is, if you ask them, what's your favorite part of the job? I don't know anybody who has ever said, oh, I love the grading. So that would include me. I'm not really wild about it. So, well, if I'm not wild about something, my strategy is usually to like get it over with. I like jump into it. So I got them graded pretty quickly. Guys, the homeworks will be graded out of 20 points always. And just so I want to make sure everybody understands how this works. What I do is I break that into sort of 2 parts. I give you some points just for doing it. Basically, everything could be wrong. But as long as you've attempted the problems and made a submission of the problems, I'll give you some points. And that's usually in the ballpark of, I don't know, 6 or 8 points, something like that. So let's just say if it might be 6, as long as you turned in a complete thing, I'd give you all those points, regardless of whether it's right or not. And then what I would do is, okay, well, the difference with 20 would be 14 in this example. I just go through and I grade enough things until it comes up to 14 points. And it also depends a little bit just how busy I am that week. If I'm like pretty busy, I might grade fewer problems, but then try to make them worth more points, or I'll try to grade more problems and make them worth less points each, whatever. I just figure that out. And I kind of do it randomly as to which problems I'm going to grade and which ones I'm going to just have to let you read the solutions for. But normally, especially with a class this big, I probably will not be grading every problem from every assignment. I do know some diehard professors who managed to do that somehow. It's not really easy enough for me to manage all of that. But I do, of course, post the solutions in Canvas. If you go into Canvas under the files section of the website, one of the folders in there is homework solutions. So I've already published the ones from the first assignment that you had turned in last week. And so, you'll get some score here. Let's just make up something. Let's say you got 12 out of 14. I'll usually try to tell you if I take something off, I'll usually put a note as to what the problem was. And then over here, of course, I just add all of that up to get a final score. Back in the old days when I wasn't very smart, I put an equal sign here. And some students said, wait a minute, this is less than 1. And this is 1. How can that add up? It doesn't work. So I stopped doing an equal sign and put an arrow. They're much happier with that. Anyway, if you ever have an issue with the grading or if something goes awry with anything, some pages don't scan or something like that, just let me know. We can always talk about it. I don't promise to change your grade, but I'll at least have a conversation with you, make sure it's clear why you lost points. Conversely, even if you got a perfect score on your homework, it's still not a bad idea to go read through my solutions, because first of all, I didn't grade everything. So maybe there'll be some problem that didn't get looked at that you want to make sure you were doing it right. And secondly, even if, I did grade it and I gave you full points for it, it's never a bad idea to maybe hear a different perspective or read a different perspective. It gives you maybe an idea of like maybe what I would consider a good standard of a write-up for something. One of the challenges with combinatorics too is these write-ups. One person might spend an entire page to explain something that somebody else thinks just deserves 1 sentence, right? And it could be that they were both being honestly legitimate. That's what they thought was needed. So it does take like a little bit of calibration, I think, to kind of get the hang of what's a good explanation or write-up for some of this stuff. So doesn't hurt to look at my solutions. I'm also piling up the videos of our lectures. I'm doing another one today. And in Canvas, there's a pages section where you can click on the class lectures. If you need to go back and review anything, you can do that at any time as well. Okay. Well, I don't think I hardly need to say this, but just for the record, I will. Today is the last day that you can actually drop this class. Like, I'm not encouraging anybody to do that, but I just feel like I should tell you, it's the last day you can drop any class without getting a W on your transcript. So for those of you who were waffling about it, you need to stop waffling soon, unless you want to have it on your record, that you were at least here for a little while. And then one other thing I wanted to mention, I tried to get this going last semester and I failed. Basically, it was total failure on my part. I was just too busy. Before COVID, we had a math club at Cal State Fullerton. We had a sort of a group of, sort of a core group of math majors that wanted to sort of have a organization that was structured around math, but it wasn't just all about math. It was also a social group. It was a chance to sort of belong to a community. We had this pretty nice club for a while. We would go to conferences together. We would play games together. We would do all kinds of practice our talks with each other. If we were going to be doing presentations, like stuff like that. It could be anything, whether it was academics or whether it was just for fun, didn't matter. And then, of course, COVID hit. And we all went home. And for about 3 years, everybody was just kind of just trying to keep their head above water. And it was hard to get anything going again. And I was the advisor of this math club for quite some time. And of course, I also went home. So the club kind of fell by the wayside. And it's taken a while to kind of get back. And even the first couple of semesters when we came back from COVID, it just seemed like things were different. It's like, oh, it's still pretty quiet. People are mostly just commuting in and out. But what I have really noticed in the last couple of semesters is a much greater activity around McCarthy Hall. More students spending more hours here to work with each other, to study, to just take advantage of the space that there is to work. And so and now that I'm back as well, I thought, well, maybe we should try to resurrect this math club again. So what I'm going to do, and it's not just going to be me, there is another professor who's going to help me with this. Dr. Cito is also a pure mathematician. And on Thursday, this Thursday, and you may not be able to make it, in which case you can certainly talk to me outside of this meeting, but we're going to have a brief meeting on Thursday right outside of my office. There's already at least 10 people that Dr. Cito has told me are going to come. So I think there's going to be a few people on Thursday outside of my office. So that's down in the basement of the building. And this is just going to be kind of an organizational meeting to discuss, first of all, vision for the club, who's interested in maybe either participating as a member or whether you would like to actually be an officer for the club, because technically we can actually have this club on the books in the university's structure. With an account through ASI, we can have money, we can spend money, we can do fundraising, all kinds of things. And so if you're interested in kind of being a part of that, of resurrecting our math club sort of in this post-COVID era that we are in, I am interested in doing it. I've always enjoyed this particular role. A lot of faculty get stuck on these committees that are all about, boring administrative service stuff for the campus. I sort of got away with doing this, and I was like, ooh, this is like, I get to hang out with the students and I get to do fun stuff. And that's much better than what I hear some of my other colleagues having to deal with. So I'm like, yeah, I'll do that. So anyway, Dr. Cito and I are going to see if there's enough interest to get this started. If we show up on Thursday at 12 o'clock and there's nobody there, well, maybe that's our answer, right? And maybe it's not time to do this yet. But I'm gonna give it a shot. Let's see what's going on. So just think about it. And if you're free, come on Thursday from 12 o'clock to 12:30. And if you're not free, but you are interested, just shoot me a little email. And I will get you in the loop about what our plan is and what kind of activities we're going to be looking at. Probably we'll try to figure out who really wants to be part of the leadership of the club and what kind of things maybe over the next few months do we want to do. Okay, so that's just a totally on the side social thing that I thought I should mention today. Okay, great. I think that's everything announcements wise. Does anybody have any questions for me about that? Is it still hot outside? Someday it's going to cool off. I don't know when. I was going to go out hiking last weekend and I was like, I'm not driving my car any distance, 110 degrees to try to go hiking in this weather. So I basically did nothing. So I'm hoping it cools off. Anyway, let's remember, of course, this is a Tuesday. We have to go back 5 days in our memory banks and remember where we were last week when we kind of wrapped up class. I was talking about multi-sets, which means these are counting problems where repetition is allowed. And I first was talking about k different types of objects, and we're talking about permutations. Of course, for permutations, well, that means order matters. So this is the situation where order matters and where repetition is allowed. And so if I have k different types of objects, and I'm going to make an R permutation out of them. Remember, when you're doing permutations, I don't mind drawing slots for that because the order matters. And so first slot, second slot, third slot, it's okay to draw it like that. And each one of these slots, you know, has k choices because there's k different types of objects, and we have infinite repetition of those objects here. Okay, so we're assuming if there's no repetition of the objects, then we don't have a multi-set, then it's just a set, and we would have a falling factorial, right? K minus 1, k minus 2, so on. But if we're allowed to keep making the same choice again and again and again, then we will have k raised to the power of r different r permutations of that set. Okay, so that is just a quick theorem that we wrote down last time. I want to just kind of get our juices flowing here with this example, this warm-up problem here. So let's just read this together and we'll try to work it out. It's about license plates. So of course that is a situation where order matters. And so what is it saying here? A witness to a hit and run accident is trying to make a report on the license plate. Apparently it was 3 digits followed by 3 letters. They got enough of a look at it to figure that out. So let me actually, I haven't even finished reading the question yet, but I always like to just kind of set up the stage for this. 3 digits and then 3 letters, right? So these are going to be digits and these are going to be letters. Okay, so we're talking about permutations here. We're going to be counting permutations. Now, specifically, the digits 4 and 9 were observed, but the witness didn't know exactly which position. So they just know there's 4 and 9 somewhere. And that there were no vowels at all. So the vowels, of course, that would be A, E, I, O, U. You can tell this is a really fake problem. Can you imagine witnessing an accident and the thing you noticed was there were no vowels? And you don't know what letters they were, but you know there were no vowels. It seems a little odd. But anyway, just work with me here. So we're gonna try this this problem. How many plates are possible? That's actually a question. And question, yeah.
Should I be included?
Is it a vowel?
I don't know.
Sometimes.
It is? I guess it is. All right, never mind. No. No, these are the vowels. Thank you. Okay. So I can kind of sense, you know, this is not just a clear-cut problem where, you know, it's just, oh, this is just a, you know, a permutation or a combination. There's sort of some sense in which, you know, the order maybe does matter, and maybe some sense in which the order doesn't matter. So it's a little tricky. But there are some subtasks to making a license plate that has these conditions that we might want to think about. Does somebody want to outline for me at least one of the things that is in your thoughts about what we would have to choose here? Yes, what was your name again? Mitchell?
Yes.
Yeah.
I did have a question about numbers 4 and 9. Included because that with repetition or no?
It doesn't say, and if it doesn't say whether the 4 and the 9 could be repeated, then you should assume, well, that might be possible. As long as it contains the 4 and the 9, anything else goes. So it could be that there's 2 4s and a 9, or there could be 1 4 and 2 9s, or maybe there's 3 different digits. Good question. Does somebody have a thought here? Nikolai?
I was thinking one of the digits could be digit 0. And, 2.
Okay, so we know that there has to be a 4 and a 9. The third digit, right? It might be another 4 or 9, or it could be something totally different. I actually would recommend, because I'm having a hard time accessing the calculate, wrap my head around counting that. I would actually recommend whenever I have a counting problem that's too hard for me to think about, I try to make an easier counting problem by breaking this into cases. So one case would be that the third digit is a completely different digit, right? So I would probably sort of want to come over here and maybe think about case 1, that we have 3 distinct digits. Right, we already know that one of the digits is a 4 and another of the digits is a 9. So if we had 3 distinct digits, what other choices would we need to make in this case? Hmm?
You need 8. Yeah. 8.
Okay, so choosing what is the other digit, right? So there's 8 choices for the third digit. Okay, I don't know what it is, but in my head, I'm now imagining that I've fixed that digit. Maybe it's a 3. So I have a 3, a 4, and a 9. What other choices do I need to make with respect to arranging the digits then?
Where they're placed, like in the digits place that you have there, you have to whether it's gonna be in the first spot, the second spot, or third spot.
Okay, so if I have a 3, a 4, and a 9, right, there's 3 factorial ways of putting those 3 digits into 3 slots, right? So
Yeah.
let's put that down, 3 factorial ways to place the digits. Okay, and actually, that's about all you have to do with the digits if they're distinct, okay? But we of course know, and I'm gonna write down another case, and I'm not thinking about the letters yet. I'll come back to that in a minute. So by the multiplication principle here, we get, what is that, 8 times 6, right? This would be 48. 48 3-digit arrangements. But again, that's not taking into account the letters. Do the letters affect the numbers at all? Is there anything over there that says that which letters are in the license plate somehow hinges or affects or
No.
depends on what the numbers were? No, these are 2 independent things. So you can literally think of it as 2 problems, guys. It's like, how many 3-digit license plates contain a 4 and a 9? That's one question. And then the second question is, how many 3-digit license plates consist of letters that are not vowels? And you just solve both of those problems separately and then multiply the final results, you see. Okay, so I'm currently working on the first problem, which is just how many ways are there to figure out what's going on with the digits? Could be 3 distinct digits, in which case there would have been this many potential arrangements. So what else, what would be another case? If there's not 3 distinct digits, then what would we do?
What
Two
the
of
other
the digits.
digit is. and it's-
Well, you've either got 2 4s and a 9, or you've got 1 4 and 2 9s. Honestly, it's not that bad. You couldn't just write it all out, right? So the digits must be, we can actually write them all out. The digits must be, so what could it be? It could be 2 4s and a 9, so 4 4 9, or 4 9 4, or 9 4 4, right? Or it could have been 1 4 and 2 9s, so it could be 4 9 9, 9 4 9, or 9 9 4. If there was a repeated digit, it has to be either a 4 or a 9 that repeats, and there's exactly 6 of these. So there are 6 of these. So when I do various counting with different cases, what do I generally want to do with the sort of the numerical results of those cases? Absolutely add them. That is absolutely right. We are gonna add these together. So summing, and these are the only cases there are, right? We've covered everything with the digits. Summing these cases, we get, well, it's 48 plus 6, right? Which is 54. Let's just call them digit configurations. So this witness gave us enough information. The witness to this hit and run gave us enough information that we have only 54 potential license plates with respect just for the digits. If we only were wondering what the digits could be. Does everybody agree with that? Yes.
What if you just did like 2 cases, you just did it all in one case where it's like instead of 3 distinct digits, the last one would be anything. So there's 10 digit or 10 choices for the 3rd digit, and there's still 3 factorial ways to place the digits, but that's 60 and it's not 54.
Right, it's because that's over
Do
counting.
you have to subtract the 6 there, because they get counted twice in that situation, so the 6 in case 2 that we have, those get counted twice, so then we'll end up with 54 ways.
60 minus 6. Do you remember that problem I went over last week? That I said, how many poker hands had at least one club? And I gave the wrong answer where I sort of said, well, what if you just choose a club first and then you fill out the rest of the cards in your hand? That first club, right, might be, it could have been that you obtained that first club in the 4 that came later, and that one of the 4 that came later was the first one, and so you've actually put things in order that you didn't mean to put in order. And that's kind of what you're doing here too. If you're sort of saying, well, I'm gonna assume I have a 4 somewhere, and I'm gonna assume I have a 9 somewhere, right? And so now I can have anything here, right? So there's 10 choices there for that digit. But then you're gonna multiply by 6 because you're permuting all of these around. But let's say that of these 10, you happen to pick another 4, right?
You switch the order, it's the same thing.
That would have been exactly. So if you had sort of started off with those 2, right? And then you say, well, there's 10 choices here, but then if you chose this 4, then you're counting this one twice. Yeah, it's subtle issue there. Okay. Okay, let's talk about the letters. I think the letters is a little easier. All it says here is that there are no vowels. Okay, so the number of letter configurations is, does somebody want to try it? Yes, Christian. Yeah, we're using this theorem right here. Yeah, this is a relevant result here. So we have a multi-set with 21 different kinds of objects, right? Everything except the 5 vowels. And you can have as many of them as you want, and you're making 3 permutations of those. So R is 3, K is 21. So this is 21 cubed. So you could just say C theorem 2.4.1. Honestly, I don't often reference the theorems. I just kind of, in the flow of the solution, I just write these things down. It's just kind of natural to me. So this would be 21 cubed. Was that a hint?
Yeah.
Please.
So I know that, I think last time you covered the case for the theorem when you would just need to have an R amount of each object for it to work, right?
Yeah, and of course with license plates, you can use as many
As many as you want.
as you want. That's right. Yeah, you can have the same letter again and again and again. So then, are we done? By the multiplication principle, the final answer is, what would it be? 54, right, for the digits times 21 cubed, and I don't know that I came up with a number for that, and I really don't need to worry about it. Yeah, that's, I'll just leave it at that. I'll just leave it at that. Yeah, Jose?
Instead of using the theorem, and we use like the combinations, right, and just subtract like what's left. So for instance, like the first one, right, we have 26 possible choices, and then we have so many vowels, right? And then like the next one,
Yeah, well, that would, oh, I see. So you would just take 26 cubed and then subtract the ones that contained at least one vowel. You can do that. It's definitely harder than this, right? And this is not a case where the subtract or the complementary problem is easier. This case, the easier problem is to just take out the vowels to begin with and count exactly what you want. It's 21 cubed. Yeah, you could. I'm sure you could rework it as a subtraction as well, but it would be a bit of a pain. There'd be overlap. There'd be something called inclusion exclusion, which we're going to talk about soon. That you'd also have to address there. It's definitely more complicated. What if we didn't know that it was 3 digits followed by 3 letters? So the witness knows that there were 3 digits and that there were 3 letters and that these constraints were included. So no vowels, has to be a 4 and a 9. What would we need to do if we didn't know that it was 3 digits followed by 3 letters? We are going to multiply by something. It's not just 2.
Still stringing the letters and the digits.
No, they're not strung together. So I could have a digit and then a letter and then another letter and then a digit and then a letter and a digit. I don't actually know. So let's just put this
6 factorial.
6 factorial? No. Let me phrase the question, let you guys think about it for a second. So the follow-up is, how does this change? How does this change if we don't know which positions the digits are in? So in other words, I'm taking out one piece of information, which is just which of the slots has the digits and which of the slots has the letters, but everything else about the problem is the same. There will be this many ways to configure the digits into whichever slots they are. And there will be this many ways to configure the letters into whichever slots those are. But what's the one new thing that we have to choose now? Notice I said the word choose.
6 spots, we have to choose 3 for the vowel, or 3
Yeah,
for
okay.
so then
3 for the digits and then the other ones would be for the letters or vice versa. Exactly. So the answer here, does that make sense to everybody? We have one more thing to choose here, which we can do at the very beginning if we want, is we have to take into account that there are 6 choose 3, right? Which is actually equal to 20 if you work that out. There are 6 choose 3 equals 20 ways to decide which slots will have the digits. I'll just say digits. Because by default, the other slots then must be letters. You don't have to make any more choices. So then in that case, your final answer is just going to be, so in this case, so we get a final answer here, you guys are with me on this, a final answer, which would be 54 times 21 cubed, and now we would have a tack on another product of 20 there, okay? And again, I almost prefer the answers written this way, because then I can see how the factors were put together to make the final answer through the multiplication principle. Okay. That sounds good to me. Let's see where I'm at here. Yeah, okay, in a few minutes, we will practice this a little bit more. Question first. 52 cards.
One of the problems.
Uh-huh.
But normally when cards out. It make more sense to have something like that. 52 is 13 times this, you know, if you subtract 13, choose again. Or we can do like 52, choose one. And individually subtracting one every time to have that sum.
I think the first thing you said makes more sense. So you take the 52 cards, you're gonna divide them into 4 piles and give one pile to this player, one pile to this player, one pile to this player, and so on. So you're choosing, because you don't want to put the cards in order, right? So I would say take the full deck, choose 13 of them to give to player A. So that's 52, choose 13. Then you have 39 cards left. Choose 13 more of them now to give to player B and go around the table that way.
But I'm
Yeah.
just thinking like second, third percent. Or the first person given cards. Superstition. Cards.
Uh-huh.
So,
I don't think it's supposed to be thought of as in terms of like trying to win the game or anything. It's just like how many ways are there to like pass out these objects? So I wouldn't put yourself in the role of any of the particular players there. Yeah. Yeah. Absolutely. So that would be the same as this value, which is 20. So that is more or less how this is calculated, in fact. So yeah, you could think of it that way. So just purely from the formula, from a numerical point of view, I'm on board with that, right? So you can do this from the factorial point of view. I think in terms of the concept of deciding which slots would have the letters versus the digits, I tend to think of it more as this expression. I'm just choosing the slots. I'm not, when I have lots of factorials around, it's sort of like, well, I'm putting everything in order and then dividing out by that order somehow. So I maybe wouldn't think of it that. Actually, you bring up a good point that's kind of related to what I was going to talk about next. So maybe I'll do that. We're going to do some group work here in a little bit too, but I think maybe I'll talk about multiple ways of thinking about some of these combinations and permutations relationships. And it basically comes under the heading of what I'll call this little complication. I've already kind of mentioned this before, guys, but I just want to get some of this into the notes now, which is namely, what if the order of the objects, right? So what if the order of the objects, I'll just put this in quotes, guys, sort of matters. Or, partially matters. And there's an example that is kind of a classic one, and I've even mentioned this before. I'll just actually put it up here as an example now. Like, so, because yeah, whether order matters or not determines whether you're talking about a permutation or a combination. But what if it's kind of somehow a little bit fuzzy, right? What's going on? So here's an example of a fuzzy problem, right? How many ways are there to arrange the letters of the word Mississippi? Right, so this is kind of a classic example. And so I'm actually going to kind of solve this in 2 different ways. So I'm going to do solution number 1 and solution number 2. And so this is perfect timing for Maddie's question, because she was thinking about, like, instead of thinking of the combinations, could I think of somehow factorials, which reflects permutations, and do some like correction based on that. And that's exactly what sort of the 2 ways of looking at this would be. So the first solution to this problem would be to just imagine that there's actually 11 different letters. I know that these are, obviously, some of these are the same, but there are 11 slots here that I'm gonna put these letters into. If these letters were all distinct, and so we could actually make them distinct. We could say, well, this is gonna be the I1, S1 and S2, I2, S3, S4, I3, P1, P2, and I4, right? We could like subscript each of our letters to make them actually distinct. And if it was 11 different objects, so if we had 11 distinct letters, right? If they were all distinct, then we would have, can somebody tell me how many arrangements there would be for an 11-letter word where there were no repeated letters? 11 factorial, exactly. So there would be, we would have 11 factorial arrangements. So we can kind of start from there. And then what we have to do is accept the fact that there's really not that many because the identical letters don't look different if you switch them. In particular, so this would be one of the 11 factorial arrangements. If I were to swap the two P's, right? Now, those would be counted as two different arrangements if we were in the situation of 11 distinct letters, but as soon as they're actually the same, then actually for every arrangement where you have P1 to the left of P2, there's going to be another corresponding arrangement where P2 is to the left of P1. You just swap those two letters, leave everything else the same, just swap the two P's. So that means you have doubled, right? You have doubled how many arrangements you really want to count here. And so we fix that is by, well, multiplying by 1/2, or in other words, dividing by 2. So we will divide out, by the letters that kind of look the same, right? So how did I actually want to say this? We will divide out by letters that are identical. Identical, I can spell today. So I'm just going to say 2 factorial, and this would be to handle the P's. We'll start by talking about the P's. And then, well, we also have 4 I's. And you see these 4 particular positions, right? Slots 2, 5, 8, and 11. If I have 4 I's in those slots, there's actually 4 factorial ways to permute those I's if they were 4 distinct objects. So I'm going to divide out by a 4 factorial as well, and that's going to be for the I's that are the same. And then also the S's are the same. So I'm going to divide out by 4 factorial for that. And so my answer, so we get an answer now from this, guys. The final answer would be to start with the 11 factorial and divide by 2 factorial, 4 factorial, and 4 factorial. That probably feels a little bit like, Maddie, what you were saying. If instead of thinking of this as 6 choose 3, we think of it as 6 factorial and then divided by 3 factorial and then divided by 3 factorial again. Exactly. So it's sort of like, you know, my license plate has 3 digits and 3 letters, right? If this was really 6 different letters here, there would be 6 factorial ways to arrange those letters, but we're not really keeping track of, like, you know, the distinction between the slots that have the digits. So I would divide by 3 factorial for the D's and divide by 3 factorial again for the L's. And that comes out to 6 factorial divided by 3 factorial and divided by 3 factorial again. There's actually a notation for this. So there is a notation here. I want to get this down for you as well. We kind of can use a combinatorial notation that looks like those combination expressions where we just put the 11 on top. And now on the bottom, we just put all of those numbers, the 2, the 4, and the 4. So you can just imagine doing something like that. Okay, so that's just an alternative notation. That's one way to think about the Mississippi problem. But there is another way. And before I go on though, are people following my reasoning here? Jose?
Just, how did you choose the? Again?
This?
Yeah.
Oh, I was just kind of trying to make my letters look different. So this is the first I, this is the second I, this is the third I, this is the fourth I. I'm just kind of labeling them that way. Yeah, that's kind of just to pretend for a minute that they actually are distinguishable from one another. Yeah, but there is another solution here. Oh, sorry. Yeah. Well, this doesn't quite work, but that's because technically there's an M. So I could put a 1 there. And of course, putting a 1 here would not probably hurt anybody's feelings, right? This is not changing the value at all. So you can do that, and and that's exactly right. So feel free to take advantage of that. Okay, so that's actually good. I'm actually glad you suggested that. It's probably a good idea. In fact, before I present solution number 2, let me state a little theorem here that I think will be useful as well. So this is a second theorem here today, guys, that I'd like to write down. So let S be a multiset with K different types of objects Now, remember, there was another theorem a few minutes ago that started off just like this. Let S be a multiset with K different types of objects of infinite repetition. The number of R permutations is K to the R power, right? Here, however, I'm not going to allow infinite repetitions. After all, I only have 4 I's. I only have 2 P's. I have limitations on how many times, like if I'm trying to solve the Mississippi problem, I cannot start solving that Mississippi problem by writing down 2 M's. Okay, I am restrained to only have 1 M in my permutation. So this theorem is now going to address this kind of a problem. So K different types of objects with finite repetition. Okay, so with finite repetition, I'm going to call them repetition numbers, if that's okay. These would be numbers that we could denote as N1, N2, and so on up to N sub K. Okay. And by the way, on the Mississippi problem, K is equal to 4. I have 4 types of objects, right? The repetition number for the M's would be 1. The repetition number for the I's would be 4. The P's would be 2, and so on, right? So that's the setup of this. Then, let's just say respectively here, doing everything in order. Okay, then the number of permutations. Notice I'm not saying R permutations, I'm just saying permutations. That's because I'm going to do permutations of all elements of S. Sorry, I know it's a lot of writing. I'll slow down. Okay, so the number of permutations so you're going to actually permute all of them. Okay, and the answer will simply be, I'm sure you can figure this out. You add up all of these repetition numbers, N1 through NK, and you do a big giant factorial on that. So on the Mississippi problem, this would just be, 1 plus 4 plus 4 plus 2, the same numbers that you see down here, right? So you'll be adding those up and doing a big factorial of those, and then you'll put N1 factorial on the bottom, and 2 factorial on the bottom. You divide out those factorials because what you're doing is you're saying, no, those objects are not really distinct. Okay, they're actually identical. And this is equal to, notationally, what I already kind of introduced in the Mississippi example, where you just kind of use the same combinations notation, but you allow for multiple numbers on the bottom row. So now this is consistent with what Maddie was just saying, which is that the numbers on the bottom But she was pointing out the numbers on the bottom should add up to the numbers on the top. And now they do. Okay, so it's absolutely a perfect lineup with what we had in that example over there. Okay, so that's the theorem on that. But I do want to show you a second solution to this problem because I find that just about 50% of people prefer this solution and 50% prefer the other solution, which is enough of a balance on both sides of the coin that I should show both. Because it's helpful to see different perspectives, and it might just be for some of you, it makes more sense to think of it this way, which I'm gonna now explain here. So the solution number 2 to the same problem, okay? So the way this is gonna work, guys, is we're gonna have our slots here. Right, so we start with 11 slots, which is where we're gonna fill in these letters, and we just start choosing this, choosing the slots to put the different letters in. So there are 11 choose one ways to choose a slot for the M. We only have one M. So it'd be 11 ways to choose that slot. And then we would have only, how many slots would be left? 10. And I would have to choose 4 of those slots. Just do a little ditto symbol here to make slots, to choose slots where I'm going to put the I's. The fact that I'm saying the word choose is in respect to the idea that the order does not matter, right? All that matters is which slots have you hand-picked for the I's, because then it doesn't matter whether you've got 4 I's and 4 slots. It doesn't matter whether which I goes in which slot, because they all look the same. Right? It doesn't matter what order you fill those slots with those 4 I's. Okay, so there's that. And then after we have done that, how many slots are left? 6 slots are left. I now have to choose 4 of those to fill in with the S's. And then finally, we would have only 2 slots left. And of course, I have to choose both of those. So you're not going to be actually making any choices about the P's. You're just going to write them down in whatever the last 2 slots are that are left over. And so, again, I have 4 subtasks of filling in a arrangement of Mississippi here. And so the total number of ways of doing the whole task would be obtained from the multiplication principle. So by the multiplication principle, there are 11 choose 1 times 10 choose 4 times 6 choose 4 times 2 choose 2 ways to complete this. Okay, if you were interested, you could actually write out the factorial versions of n choose k for all of these. And you're going to notice a lot of canceling going on, and you should be able to rederive the answer that we had obtained over here. It's going to be the same. And yes, Jose?
These are permutations, right?
This is a combination. These are combinations.
Okay.
Right?
I was just making sure because like
Well, since the order sort of matters. That's the issue here. So what we're saying here is that the order. Correct. So I'm choosing 4 slots to put the I's in. But I'm not putting those 4 slots in order. I'm not saying, well, there's 4 distinct I's, and so it matters which one's first, second, third, and fourth, right? They're all identical. So there's really only one. Once I've picked 4 slots for the 4 I's, there's only one way to put them in that slot.
so you kind of decide if like the order matters, right? Then notice that in some of the problems you're like, all right, if you think about it, like, do you want the order to matter? So then we could choose to For that.
Yeah, like here, you're sort of forcing the order to matter first by saying, I'm gonna imagine all of the letters are distinct, and then I'm going to divide out by the fact that the order only sort of matters, right? In some respect, it doesn't matter. Here, I'm kind of not taking the order into account at all, in the first place, I'm trying to account for it. By the way, of course, this answer would be the same, this would be the same as if I first chose 4 slots for the I's, and then I chose, I don't know, 1 slot for the M, and then I chose 2 slots for the P's, and then I had 4 slots for the S's. So, you know, just from a conceptual point of view, this number should agree with this number. And actually, it should also be equal to, what if I chose the P's first, right? 11 choose 2 ways to do that. Then maybe then maybe I choose the S's second. And then maybe I choose the I's third, and then we have a 1 choose 1. These are all gonna be the same.
So there.
There's how many ways are there to like do this in a different configuration? Don't confuse me. Yeah, so but anyway, you get the idea. I kind of get the idea. So what if we didn't actually want to use all of the letters? So this is Mississippi, there's 11 letters here. What if I asked you, let's just throw a little twist in this. I want to write down the 10 permutations of Mississippi. Not the full 11 letters. I want to do a 10 permutation of Mississippi. So think about it quietly, Mississippi. And then I'm going to take your ideas on how to do this. So follow up. How many 10 permutations of Mississippi are there? So, wondering if anybody has any thoughts on this? Fernando?
Yeah, so we have 11 letters total and we're trying to make it 10.
Mm-hmm.
So what we'll do is we'll account for each case where we're going to remove 1 letter from each of the categories. So if we were to categorize that as a multi-set, just doing the multi-set notation, you would just take away one when a case when you don't have an entry. Case when you don't have an on.
Exactly. So there's going to be either an I left out, an M left out, an S left out, or a P left out, right? One of those letters will be left out, and we can take each case. I would not, this isn't a situation where you're just going to like do one thing and then multiply by 4. Because it makes a difference whether I leave out the S, which there's 4 of, versus leaving out an M, which is only 1 of. So when in doubt, cases can be very effective for like taking a harder problem and breaking it into several easier ones. So let's just say if M is not used, then what we would get for an answer would be, you know, this, maybe I'll use this, a new notation I just invented. I leave out the M, I have 10 letters left. I have, out of those 10, I have 4 I's, 4 S's, and 2 P's. So I could write it like that. Again, remember that this is simply, if you prefer, this is just 10 factorial divided by 4 factorial, 4 factorial, and 2 factorial. Okay? On the other hand, as Fernando was saying, we could choose to leave out a different letter. What if the I is not used? And by that, I mean one of the I's, right? So I still have 10 letters total. And I have 1 M to place. And on the I's, if I'm not using one of them, then I only have 3 of those left. And then for the S's, there would be 4 of those and then 2 P's. Austin.
Do we need commas there?
I should be putting, I probably should put commas there. It's kind of a good idea. So this would be 10 factorial divided by 1 factorial, 3 factorial, 4 factorial, and 2 factorial. And then if S is not used, I'm just going to say it's the same, right? Because there's the same number of S's as there are of the I's. And then finally, if P is not used, That'll be a different case. If P is not used, then we would have 10 on top, and on the bottom, there's one M, there's 4 I's, there's 4 S's, and there'd only be one P if we leave one of the P's out. Right, so that's 10 factorial divided by 1 factorial, 4 factorial, 4 factorial, and 1 factorial. And now what am I gonna do with all these numbers? Add them together. Exactly, I use the sum rule. So sum them to get the final answer. Okay, that seems to make sense to me. Okay, let me throw one more problem at you, and then we're gonna probably be done with material for today. We'll get on to some group work. Yeah. Yeah, that's what I'm saying there. I can just do 2 times that. Yeah, was it?
If you ask like the 9 permutations,
Yeah, what if I asked you for the 9 permutations of Mississippi? You'd have more cases, like you would either leave out an M and an I, or an M and an S, or an M and a P, or I could leave out 2 I's. Right, there'd be more than just 4 scenarios there. Yeah, that might be good for the test question.
No.
Just kidding. Yes, you come to MH 33. Take a number and then I call you in and I take a look at it. Yeah, it's actually not, I mean, these are huge numbers, right? So you're not going to like get a whole lot of a feeling for it just from some big numerical answer. Yeah, and you know, you'll be confident enough, I think, that after a while you won't feel so uncertain about it. Yeah.
On a question like this, where you have the 10 permutations, you're using the addition rule, but could you use the subtraction rule to try and make it easier?
So,
Take the total.
but what is the total? Actually, when we add all of this up,
The 11 permutations.
well, now the trouble with that is an 11 permutation and a 10 permutation are not living in the same universe. It's not like they're different types of objects, so it's not like, you know, I'm taking all photographs and then subtracting photographs where 2 people are standing next to each other, because those restricted cases would be a subset of what I'm subtracting from. The 10 permutations are not included as a subset of the 11 permutations. So the subtraction trick maybe doesn't make as much sense when the objects are not comparable like that. It's a good thought, but in this case, I would probably just steer towards this. Let me throw one at you that's maybe a little interesting. All you teachers out there, you ever put your students into groups to work on stuff? Well, I do it sometimes. I usually let you pick your own groups, but let's say that you had 30 students and you wanted to put them into 10 groups of 3. Okay, I'd like to know how many ways there are to do that. How many ways are there to put 30 students into 10 groups of 3? Do this one together, and then I'll let you guys then we'll do some group work. I think we'll have time for that, hopefully. Thirty students are gonna go into 10 groups of 3. Think about what choices we'd have to make. It's actually going to be more than one way to think about this, I have a feeling. It's kind of like Mississippi problem has multiple ways of thinking. Anybody have a thought about it? Daddy?
a long one, but could we start off with 30 choose 3 times 27 choose 3 times.
Okay, let's try it. Maddie's idea. I don't know if everybody could hear that. I kind of like what she was thinking about. So what Maddie was suggesting here is that we take the whole group of 30 and we sort of choose 3 of them to be in a group. Okay, and that makes one group. And it's kind of nice, we're not putting them in order, because when you have 3 people in a group, there's not like a first person, second person, and third person. Everybody's kind of to be thought of as just being chosen for the group. If I said something like, how many ways are there to put 30 students into 10 groups of 3 and choose a president for each group or something like that? Well, then we would have to do some extra choosing or put somebody in order first as a president. But here we're just putting them into groups. So what she suggested was choose 3 people for the first group, and then there'll be 27 students left. Choose 3 of those. Is that your idea? Right, so choose 3 of those and then just keep going like that. There'll be 24 left, pull out 3 more, right? Doesn't matter what order you do this in, and we just keep going. And this would just go all the way down. I'll go ahead and write it all the way out. It's kind of long, but that's okay. And the last group, of course, by the time you're only down to the last 3 students, you have to put them in a group and you have no choice about it. So 3 choose 3, which is equal to 1. What do you guys think? Does that look like, I like this idea. Is that going to be the right answer? You know, let me make a suggestion to you guys as well as this is another strategy you can use kind of in this chapter and in combinatorics in general, which is that if you have kind of a big problem that is a little tricky, you could try to imagine a smaller problem. Suppose there were only 4 students and you wanted to put them into 2 groups of 2, right? 4 students into 2 groups of 2. So using this same idea, you would take the 4 students, you don't need to take notes on this, just kind of listen and then you'll see we'll adjust this one over here. So out of the 4 students, just choose 2 of them, that's your first group. And then there'll be 2 students left, choose that's your second group. Okay, what does this equal? 4 choose 2 is, 4 times 3 divided by 1 times 2 using the factorial thing. And that comes out to 6. Is that the right answer? So I'm going to take these 4 people right here. Okay. I would like to know how many ways can I put them into 2 groups of 2? So we've got 1 right now, these 2 and these 2. Would there be, what other ways could we do it? We could put Teresa and Kevin, Jose, and yeah, that's right. So we could put Teresa with Kevin, or we could put Teresa with Jose. How many groups is that? There's only 3 ways to do it. Right? So you can put A with B, and then you can put C with D, or you can put A with C, and then you can put B with D, or you can put A with D, and then you can put B with C. Somehow this number is too big, and so is this number. What is the issue? Yes.
Both here. So like A, B is one way and C is the other way. Like 6 different
Exactly. And the other way that you could imagine that we're overcounting here is we're actually putting the groups in order. Even though within each group of 3, we have not put the people in order, we have sort of with this solution, we have said there is a first group, there is a second group, there is a third group, there is a fourth group. And so not only do we have 10 groups, we have a group number 1 and a group number 2 and a group number 3. And we don't really want that, right? We're not keeping track of any ordering of the groups. So how am I going to fix this answer? Divide by 10 factorial. That's exactly the right answer. Yes, so you have to, just like here, we would need to divide by 2 factorial, and we would actually get the right answer, which is there's 3 ways to do it. Sometimes just taking a smaller version of the original problem can get you the right answer. There is another way to think about that problem. I'd like to show you that as well. I like to show you several ways because, you know, sometimes one solution will hit a student a whole lot better than another. Okay, I got another way. Oh, sorry.
Sorry, why did we do 10 factorial again?
Because we're trying to unscramble the 10 groups. So instead of first group, second group, third group, fourth group, fifth group, those are like all in order. So I'm taking 10 things that are currently in order, which there would be 10 factorial ways to put them in order. And I'm trying to say, no, 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 that's only one arrangement.
Okay.
Right, exactly. Good question. Is everybody okay with that? So, you know, basically, this is choose students for groups. I like to give little reasons here on the side, and this 10 factorial is remove order of groups. So you have to be careful. There's the ordering of the people within the groups, but then there's also ordering the groups themselves, and we don't want to do either. We don't want to do either. Okay, so maybe you don't like that solution that well, or I hope you understand it at least, but if you are not feeling great about it, I can give you another way to think about it. What you can do if you want to put these 30 students into 10 groups of 3 is you can start by laying out 30 chairs. And now I'm kind of putting these in order. And you just tell the students, sit down in the chairs, right? And there would, of course, be 30 factorial. I got 30 students and 30 chairs here. So this is a second, so this is solution number 2, sorry. Sit the students in a row of 30 chairs. And that's how many ways there would be to do it. 30 factorials. Yeah, I'm really keeping track of the order now, right? So there's 30 factorial ways to sit students in chairs. After you've done that, what you do is you just come along and you just draw dividers between these chairs 3 at a time. So you basically are going to say, all right, whoever's in the first 3 chairs, you're a group. Whoever's in the second 3 chairs, that's a group. In the next 3 chairs, that's a group, and so on. Okay. But now, of course, this time, you know, if, you know, Alice and Bob and Charlie are sitting in the first 3 chairs, Alice, Bob, and Charlie here. Of course, if those 3 students scrambled within those first 3 seats, they'd still be a group and it wouldn't be any different. So if it was Charlie, Alice, and Bob, or if it was Bob, Alice, and Charlie, right, any of those would be fine. So I need to take out 3 factorial for Alice, Charlie, and Bob reseating themselves within the first 3 seats. And I have to do that for each threesome along the line. And so that is actually 10 powers of 3 factorial. So you would have to remove this 3 factorial 10 times. And what that does is it takes out the ordering within the seats. But of course, we still have the same issue that we did in solution number 1, which is what if Alice, Bob, and Charlie sat in these 3 seats? Then that's the same group of those 3 students as if they were sitting here. So I need to take the order out of the groups as well. So we still have the 10 factorial that we have to divide by. Okay, so this is the 3 factorial to the 10th is to unorder students in a group. And then the 10 factorial is to unorder the groups themselves. Yeah, so we have to do both of those things. And that's just another alternative solution that you could have. Okay. think we're gonna just wait until next time to do the group work that I brought. Nikolai?
Can you also do this thing similar to solution?
If you take 30 permute 3 times 27 permute 3 times 24 permute 3 and so on, that is 30 factorial. Yeah. So yeah, and that is basically, you're basically thinking of viewing it in the form of this, and then the 3 factorial for each of those factors is turning the permutation into a combination. So that's a good connect, guys, it's good to see the connections between these numbers. It's good to sort of recognize that, all right, that's gonna be the same thing as all of this. Yeah.
Oh, okay.
So one little fun fact about, so I think we'll wait on the group work, but one little fun fact about me, I think it's so funny, if you've been in my class before, I've told you this before, but I haven't told most of you this, that when I was growing up as a kid, I watched soap operas. So I would go to school and then I would come home and my mom would be there and we would just, before I started on my homework, I always wanted to kind of just relax, soap operas are really kind of, you can just kind of be half awake and just kind of like take a little snooze before I start working on my homework and stuff. So I would do that. Kind of got hooked on these things. But you kind of know how soap operas are, like the storyline keeps going to the next day and so on. And by the time you get to like the end of the particular show, like usually something dramatic is about to happen. Like there's supposed to be like some, tense music coming up and something to get you and what's going to happen next? I wonder what's going to happen next. So maybe it's because of that I watched soap operas when I was growing up, that I've sort of developed this thing with my teaching, which is that I have to give people like a reason to want to come back. Like something that we're going to do next that's going to be exciting, that you'll come tune in again next time. And I can tell you that on Thursday, finally, this Thursday, if you'll come back again, right, I'm finally going to have time to talk about combinations of multi-sets. You notice here, we've been putting things in order today, right? The Mississippi problem, the order of the M's, I's, P's, and S's matters, right? But what if the order doesn't matter? What if I go to the grocery store and I have as many apples as I want, they're all identical. They all look the same. And I have as many oranges as I want, and I have as many peaches as I want. And my mom sends me to the store and she says, come home with 20 pieces of fruit. I don't care how many of each kind you bring, right? But I can tell you that, first of all, you're allowed repetition because you can pick up multiple peaches, they all look the same, multiple apples, they all look the same. So repetition would be allowed, right? But the order doesn't really matter now. The order part is, so we have a multi-set, repetition being allowed, that means we're talking about a multi-set, but the order doesn't matter in the sense that when you come through your mom's front door with the fruit, she doesn't care if you picked up all the apples first or all the peaches or whether you ran around and did a big mixture of whatever ordering of them that you wanted. The order doesn't actually matter there. All that matters is what you ended up with at the end of the day. So that is a situation where we're talking about a combination. So combinations of multi-sets, we actually have not talked about that kind of problem yet. So on Thursday, I'm going to do that. It's a pretty cool thing. It's called Stars and Bars. We'll do that next time. And I'll leave that at that. My soap opera is over for today. Guys, have a wonderful rest of your Tuesday. I'll be downstairs if anybody wants to chat about anything.
Yeah, meet that, like those.